The goal of our project was to build software that would allow our drone to compete in Robot X Maritime Challenge's UAV replenishment task. This task needed our drone to take off from a boat, fly above and identify 2 landing pads, fly to one of the landing pads and pick up a tin can, fly to the other landing pad and place the tin can within the helipad before landing back on the boat.
And for the hardware components of the drone, we have the Jetson Nano, the lithium battery that powers the drone, the Pixhawk flight controller, forward-facing ArduCam and downward-facing ArduCam, the GPS module, and the motors, and finally the transmitter.
Our first few flights were to test the dynamics of the drone. We needed to make sure that it flew properly before we added processes to its computer. The next flights were to build a dataset of the landing pad by taking pictures mid-flight. The last few tests were to test the implementation of the object detection model on the drone live and offline. These tests were crucial in our development process, even if we had some oopsies. We may have momentarily scared our leads at Triton AI, but rest assured, the hardware damages were minor and the drone was still fully operational.
Throughout this project, our dataset went through many evolutions. Originally, we wanted to train a computer vision model to detect RGB tin cans. So for this, we started gathering a dataset by placing the tin cans against the concrete background and taking pictures with our iPhone. So then, we switched to a new computer vision task where we decided it would be better to detect the helipad instead, because the RGB tin cans could be handled by a simple OpenCV algorithm. However, because we stitched 6 boards together, it had a few artifacts that were not entirely accurate. So for the third stage, we actually managed to get a landing pad printed, which was the accurate size, color, shape, everything. We trained a YOLO V5 model using these ArduCam images, and the detection accuracy that we got from the drone in flight was pretty impressive. So this is the final model that we decided to go ahead with. For the object detection stage, we had to start off by annotating the data sets that we had collected. We used RoboFlow to do so, and we identified 2 main targets. First, the helipad itself, and second, the circles in the middle of the helipad. We also augmented the dataset a lot, changing the contrast and exposure, adding Gaussian noise, rotating it. Our model was also able to work in conditions completely different from what it was trained on. So the model was pretty robust, and we hope that it'll work in actual competition.
There were challenges at every step of this project. Building the drone was a new experience for all of us. We were given all the parts necessary to build the drone, but understanding what each part did and how it all worked together took time. Controlling our drone seemed like it would be an easy task, as we had ground station software that could tell the drone to hold its position. But when we actually tried to use the software, the drone often wandered from its hold position or shook violently. But the positive side of this is that we gained more experience rebuilding our drone than we originally thought. For our computer vision algorithm, the challenge came from integrating our model onto the Jetson Nano, namely finding a YOLO version that would work well and be compatible with our hardware. The other challenge was training our model. Since our drone was not flight capable for some time and our time with the drone was limited, we often did not have a background representative of what the drone would be performing in. While we tried to control the drone using ROS, trying to implement the control code in simulator before real-world testing proved too difficult to achieve in time. Whether it was from trying to learn 3 new pieces of software that all had to work together or trying to simulate an onboard camera, simulations were a headache start to finish. At the end of this project, we were not able to complete the navigation and control software. The plan was to align the drone with the helipad, hover over the landing pad, and land. But due to the instability of the drone, we felt this approach was not safe until the issues could be resolved.
In the end, we successfully met the object detection MVP that was assigned to us by Triton AI. Stretch goals for this project include implementing the control software for the launching, landing, and autonomous navigation of the drone in conjunction with our object detection model. Between all our achievements and struggles, we learned a lot in this project and had a wonderful time collaborating with our team leads at Triton AI. A special thanks to Colin and Audie for their consistent communication and support throughout this project, as well as to Professors Jack Silberman and Ryan Kastner for making this possible. Thank you for watching.